Hello everyone. Let me begin with a simple thought. Have you ever tried using a magnifying glass to focus sunlight onto a piece of paper? At one particular distance, the sunlight forms the tiniest, brightest spot, and yes, sometimes it can even burn the paper. That distance is no accident, it is what we call the focal length of the convex lens. By definition, the focal length is the distance between the optical center of the lens and the point where parallel rays of light converge, the principal focus. In our experiment, we'll determine this focal length by actually forming a sharp image of a faraway object. And as you will see, the lens formula will help us make sense of our measurements mathematically. Alright, let's now look at how we actually set up the apparatus. We begin by placing a convex lens in a vertical holder that's fixed on an optical bench. This ensures stability so the lens doesn't wobble while we experiment. Next, we choose a distant object, something at least 10 meters away, like a tree, a building, or even the frame of a far-off window. The reason is simple. When the object is very far away, the light rays reaching our lens are almost parallel, which reduces experimental errors. Behind the lens, we place a white screen to capture the image. Now comes the interesting part. We gently move the screen back and forth until a sharp, inverted image of the distant object forms clearly. As you can also see in the diagram, the parallel rays from the object pass through the convex lens and converge at the focal point, forming a sharp image on the screen. Quick insight here, the use of a distant object is not just convenient but clever. It allows us to approximate the incoming rays as parallel, which makes finding the focal length of the lens both accurate and simple. Now that our image is formed clearly on the screen, it's time to take the actual readings. We begin by noting the distance between the optical center of the lens, point O, and the position of the sharp image on the screen. This distance is very important. It directly gives us the focal length, denoted as f, of the convex lens. But remember, in physics accuracy is everything. So we don't stop with just one reading. To improve reliability, we repeat the same procedure using different distant objects, maybe another tree, a window frame, or even a lamp post. Each time, we adjust the screen and measure again. All the measured values of focal length f are then recorded carefully in a table. Once we have enough data, we calculate the average. This averaging step is what reduces random errors and increases the reliability of our final value. Here's a quick insight. Multiple trials are like cross-checking your answers in math. The more times you verify, the more confident you can be that your result is correct. So to sum up, by carefully measuring, repeating, and averaging, we arrive at a precise value of the focal length of the convex lens. This systematic method is what turns a simple experiment into a reliable scientific procedure. Now, what if a distant object isn't available? Don't worry, physics has a backup plan, and that's where the lens formula comes in. For finite object distances, we apply the lens equation 1 by f equals 1 by v minus 1 by u. Here, f is the focal length, u is the object distance, and v is the image distance. Remember, if the object is placed to the left of the lens, the object distance u is taken as negative. To use this method, we simply measure u and v directly using the scale marks on the optical bench. Once we have those two values, we substitute them into the lens equation, and that gives us the focal length f of the convex lens. As you can see, this approach is extremely practical, especially when we cannot rely on faraway objects. It's like having a shortcut tool in your physics toolkit, not always the first method, but definitely a reliable one when conditions demand it. Quick insight, this verification method ensures that we can still determine the focal length accurately, even if the environment doesn't allow for parallel rays from distant objects. Now let's apply the lens formula to a real example. We are given that the object distance, u, is minus 30 centimeters and the image distance, v, is plus 60 centimeters. The negative sign for u reminds us that the object is placed to the left of the lens, following the sign convention. The lens equation is 1 divided by f equals 1 divided by v minus 1 divided by u. Substituting the values, 1 divided by f equals 1 divided by 60 minus 1 divided by 30. The two negatives make a plus, so this becomes 1 divided by 60 plus 1 divided by 30. Now we simplify. 1 divided by 60 plus 1 divided by 30 equals 1 plus 2 divided by 60, which is 3 divided by 60. That reduces to 1 divided by 20. So finally, 1 divided by f equals 1 divided by 20, and therefore the focal length f is 20 centimeters. Here's a quick insight: always be careful with the signs. If you forget a minus or add 1 in the wrong place, the focal length will come out wrong. So to wrap up, this worked example clearly shows how the lens equation helps us calculate the focal length step by step. Whenever we do an experiment in physics, accuracy is just as important as the result itself. Let's see how we make sure our measurements are reliable. First, the optical bench must be aligned properly. The object, the lens, and the screen should all be placed on the same straight line. If they are misaligned, the rays of light won't converge correctly and the image will be blurred. As you can see in the diagram, misalignment produces a distorted image, while proper alignment gives a sharp one. Next, always choose a bright and distant object. The clearer the rays entering the lens, the sharper the image you get on the screen. While taking measurements on the scale, avoid parallax error. This means you must look at the markings directly from above, not from an angle. A tilted view can shift your reading and introduce error. Finally, repeat your observations and record several values. Taking the mean, or average, ensures that random errors are minimized and the final focal length is more accurate. Quick insight: careful alignment and repeated trials are like double-checking your homework. They don't just improve accuracy, they also give confidence that the result you're reporting is trustworthy. So let's wrap it up. The focal length of a convex lens is the distance from its optical center to its principal focus. We can determine it practically by forming a sharp image of a distant object on a screen. Alternatively, the lens formula gives us a way to calculate f using measured object and image distances. In real life, this is more than a classroom exercise. Accurate knowledge of focal length is what makes cameras, projectors, spectacles, and even scientific instruments like microscopes and telescopes work precisely. I hope this session made you realize that behind the simple trick of burning paper with a magnifying glass lies a principle that powers the world of optics. See you in the next class, where we'll unfold another fascinating phenomenon of light.